All right, now we're on to a lab question. I really like this one. It's a cool lab design question about an R over L circuit. So students are asked to determine the resistance R of two identical resistors. They're in parallel with each other. So you can tell they must not have been able to find another way to put a equivalent resistance question on the free response. Here it is. I guarantee at some point we're just going to have to combine this and make an R over 2. They're connected in series with a battery of known EMF, and known inductance. We want to find R. On the circuit diagram, draw the voltmeter using the voltmeter symbol with connections that would allow the students to correctly measure the potential difference that decreases with time. So, there's three things in the circuit. Does it go here? Well, no, that's the freaking battery. That does not have a decreasing potential difference. That's not changing. And then we just have to really ask, is it R or L that has decreasing potential as a function of time? So let's look at each. So it's best to just look at this with some case analysis here. So again, it starts with initially no current flowing here. So it's the opposite of a capacitor. So with short times, with this RL circuit, and again, we know that this is really just the same thing as this being an R over 2. At short times, the inductor is going to oppose the changing current from turning on the switch, meaning there is a battery here, or sorry, there's a gap here. And well, for the loop rule to be true, all the voltages have to add up to the battery voltage, and while there's no voltage drop across the resistor, so that must mean all the volt drop is across the inductor. So it's a gap in the wire. But then at long times, the magnitude of the current isn't changing anymore, which means that we model the inductor as just a wire. So if we put our voltmeter here again, it reads 0. So that means that we should definitely put our voltmeter across the inductor because it's going to read the battery voltage at the start and exponentially decay to 0. Describe a procedure for collecting data that would allow the students to graphically determine the experimental value for R using a measured quantity that decreases with time. Provide enough detail so another student can replicate the experiment. Okay, well, wire voltmeter in parallel with inductor. Then start timing t equals 0 once switch closes. And then after that, you're going to collect t and v of t at regular intervals. And you're going to graph, linearize, and solve. And we'll do that later, which is why I'm not telling you how to do that right now. You could also just use the actual graph and do some either half-life manipulation or the percentage rules with time constants. Lots of ways of doing this. So now we're going to graph what we expect to get. On the axes shown in figure 2, produce a graph that represents the expected trend of the data. Label the quantities graphed on the vertical and horizontal axis. Okay, so we're going to call this V sub L. So we are graphing the voltage across the inductor, V sub L, as a function of time. Then we're graphing a line or curve that's the expected trend of our data. So Well, voltage of the inductor, we said maxes out. We'll make it more clear. We said it maxes out at the battery EMF, and then it decays towards zero exponentially, because anytime you have an inductor or a capacitor, it's this sort of exponential relationship. It also says to mark any asymptotes, so just to be very clear, it's decaying towards zero. Describe how the information from the graph would be used to determine the experimental value for R. So, from the graph, what we're going to do is, you could do some half-life stuff here, but we're actually going to linearize instead. So if you found a solution with logarithms and the half-life to get tau, great, that works too. So what you're going to do is you're going to use the fact that voltage across the inductor is equal to the EMF of the battery times e to the negative t divided by tau. Then to linearize it, since we got t trapped in the exponent, you log both sides. Apply some log properties. ln v sub l is going to be equal to ln of the battery voltage minus 1 over tau times t. And now we're graphing ln v over ln vl versus t. So now we're going to best fit. And the slope is equal to negative 1 over tau. So we're going to say best fit ln vl versus t. Those are the things to graph. And then you know that for an RL circuit, time constant is R over L. It's an R over L circuit. So that means that our slope will be equal to negative 1 divided by REQ divided by L, or slope equals negative L divided by the equivalent resistance of our circuit, which is just R divided by 2 because it's two resistors in parallel. We found that earlier. So then we can solve this and we would get that R is just going to be equal to negative 2L divided by the slope. There are so many correct procedures for this. This is just one of them. And it's definitely not the simplest. Starting with an appropriate Kirchhoff loop rule, derive but do not solve a differential equation that can be used to determine the current I in the inductor at a time t after the switch is closed. So if we look at our effective circuit here, we got EMF of the battery. U are R over 2. And U are an inductor. And then we come back. Okay. So loop rule. Well, here's the loop. Lovely. We know that loop rule says all the voltages have to sum back to 0 when we make it all around. So if we go this way, first we gain the battery EMF. Then we lose some EMF. We drop potential going downhill through the resistor. Then we drop some more voltage across the inductor. And after you do all that, I got to get back to 0. So voltage across a resistor, well, that's just Ohm's law. And voltage across an inductor, well, that's just defined as L times the IDT. And notice I've satisfied all the criteria. I have a loop rule and a differential in it, right? I have the dIdt, so it works out. And lastly, after reaching a steady state, the absolute value of the potential difference of the inductor is delta V1. They do it again, except they have an inductor with resistance in it. So the old case, well, if you have an inductor with no resistance in it, Well, after a long time, you're not going to drop any volts across it. Because if we just record the delta V across just basically a wire here, we get 0. But instead, if we look at the new case, it's not just an inductor. So the inductor still doesn't have a voltage drop across the inductor part itself, but its resistance generates a voltage drop in addition to itself. So really, the inductor sort of lives in this little box where there's a resistor in it and there's an inductor in it. And what's happening here is that even though the voltage across just the inductor part that we're modeling would be 0, well, the whole thing here definitely does. So delta V2 is definitely greater than 0. So that probably wasn't the best explanation, so let's summarize here. So with resistance, there is now a non-zero voltage drop due to Ohm's law. So delta V across the inductor is going to be equal to I times R internal, which is definitely not equal to 0. So before we said, okay, this is 0, so it's just 0, but now it's not 0. So I really like this question. I thought this was a really nice experimental design. It really tests very common skills we do with these circuits.